Hello everyone, myself Monica Chaudhary from IT Department, Acropolis Institute of Technology and Research, Indore. Today I would like to present the topic Finite Automata as a Language Translator. Before that we have studied that Finite Automata we can use as a language acceptor, because when we give some input to the finite automata it changes some state and give us some output, or we reach to the final state. If we reach to the final state from the starting state, then we say that the language or the string is accepted by the finite automata, otherwise it is rejected. But here I am saying that the finite automata as a language translator, it will not accept or reject any language, it will only translate them. Finite automata can also translate input to output, not just accept or reject but also transform string, used in lexical analyzer and compiler. On the basis of translator we have two type of machine. First one is the Moore machine and second one is the Mealy machine. In Moore machine we have the 6 tuple and output is directly depend on the current state. And there are 5 tuple in the finite automata: number of state, number of input alphabet, transition function, initial state and final state. But here final state is missing because we are not accepting or rejecting. Here we are translating the input. That's why our output function depend on the current state and the input alphabet, and the extra symbol is also added, that is known as the output function. And the same constraint are also applicable in the Mealy machine. Both machine have the same number of tuples to translate the language. But the difference is that in Moore machine output depend only on the current state, and in Mealy machine output depend on the state and input. DFA refer to the deterministic finite automata. Deterministic finite automata are deterministic if the machine read an input string one symbol at a time. In DFA there is only one path input from the current state to the next state. It doesn't accept the null move, that is it cannot change state without any input. It can contain multiple final state. It is used in lexical analyzer in compiler. As in starting I have already told to you that DFA can be used as an acceptor or translator. If it is accepting or rejecting, then we are saying that the finite automata is an acceptor. And we can classify it into two types: deterministic finite automata and non-deterministic finite automata. Now come to our topic, Moore machine. Then in table 3.8 we have the 4 number of state: Q0, Q1, Q2 and Q3. Q0 is the initial state and transition function is there, and the input alphabet are 0 and 1. When the input is 0, Q0 will move to the Q3. When the input alphabet is 1, Q0 will move to the Q1, and the output alphabet is 0. Whether our input alphabet is 0 or 1, state is Q3 or Q1. But on Moore machine we have the condition that the output depend only on the present state. That's why Q0, when we have the present state Q0, we will get the output 0. In the same way, when our present state is Q1, on input alphabet 0 we will have Q1, and on input alphabet 1 we will goes to the Q2 and the output will be 1. For the present state Q2 we have the 0 input alphabet, then we will goes to the Q2 state. If we have 1 input alphabet, then we will move to the Q3 and output will be 0 in both the state and both the cases. Or we can say that when we have the present state Q2, we will have the output 0. No matter whether the input alphabet is 0 or 1, our next state is Q2 or Q3. And the same thing with the Q3. Q3, when present state is Q3, input alphabet is 0, next state is Q3. When input alphabet is 1, then Q3, then we will move to the Q0 and output will remain 0. For example, we have an input string 0, 1, 1 and 1, and I would like to tell you one more point, that in Moore machine we have always n plus 1 string as a output. If you give the input string of length n, then we will get the output of length string is n plus 1. Why is 1 added there? Because we start from the initial state. Without any input alphabet, the present state or the initial state also give an input alphabet. That's why we have the number of n plus 1 in the output string. For example, it will be more clear to you. Let I am explain the example. 0, 1, 1 and 1. The state is given by initial state is q naught. When we apply q naught, here notice the point that initial state is q naught. On q naught state we have the output 0, means 1 0 will be count. After that, on q naught we apply the input 0, then it will move to the state q3 and output will be again 0, then 2 times 0 we have reached. After that, q3 we apply the input alphabet again 1. On 1 we will move to the q naught and q3 have the output 0, then we will get one more 0. After that we will move to the q1. When we apply 1 on the q1, we will move to the q2 and the output is 1. After that, when we move to the q1 to q2 and q2 input alphabet is again 1 and the output is 0, that's why one more 0. I think it will be clear to you. And from the table we can get an overview that in Moore machine present state and output state there is directly relation. Output state is directly depend on the present state. And in Mealy machine we have output is depend on the present state and the input bit alphabet also. From the table it has been clear to you that a present state is q1, then state is q3, on input alphabet 0, but the output is 0. And when the input alphabet is 1, then the state is q2 and output alphabet is 0. And on the next q2, when the input alphabet is 0, state is q1, output is 1. And on input alphabet 1, q2, output state will be q4 and the output will be 0. Now, how to convert the Moore machine to Mealy machine? In Moore machine, we know that the output state is directly depend on the present state. It doesn't depend on the intermediate input alphabet or state. And in Mealy machine, we know that the output is depend on the current state plus the input alphabet. That's why we have the separately two output correspond to each input alphabet. Now, Moore to Mealy machine. Now, the difference is that in Moore machine output is depend on the present state. Mealy machine output is depend on the present and next state. Then how we will convert it into Mealy machine? Notice that input alphabet q3 and 0 and 1. We have only one output at the state q1. Wherever q1 is mentioned in the intermediate state, we will write there 1 and the 0 for the other state. It will look like this table. And I would like to tell you one more point, that when we convert the Moore to Mealy machine, okay, then the number of state will also increase, because we have separately output for the corresponding input alphabet. That's why the number of state are more here. Then what is the meaning of Q20 and Q21? Q20 and Q21, there are the present state is Q2 is there, okay, but we have two different output. One is 0 and another one is 1 correspond to the Q2. That's why we have make it Q20 and Q21. And same thing we have done with the Q4. In Moore machine we have only one state, Q4, but when we notice the intermediate state, because in Millie machine the output depend on the present state and the input alphabet state, then we observe that the Q4 present state we have two different output for the input alphabet. That's why we have mentioned Q40 and Q41. When the input is 0, then we have written Q20 or Q40. When the output is 1, then we have written here Q21 or Q41. I hope it will be clear to you. Thank you so much.